Hello, Chem 1A. This is Chapter 8, Lecture Video 5, and we're going to be discussing quantum mechanics and starting our conversations about quantum numbers. So quantum numbers and quantum mechanics really helps us pinpoint an idea or structure of electrons within an atom. I like to think of quantum numbers as electron GPS, and we'll talk a little bit more about that later. Quantum mechanics was really proposed by a scientist known as Erwin Schrödinger. He is kind of the father of modern day quantum mechanics. He was the first to propose that we treat electrons as both a particle and a wave. This allowed him to use mathematical functions known as wave functions to describe how electrons move in a system, specifically a system like an atom. Now, this is a big deal. It was pretty groundbreaking. And we're not going to really get to see a lot of his equations and how he solved these wave functions, primarily because the math involved in solving a wave function is really high-level stuff. You need to have passed pretty much linear algebra to be able to get the full grasp of all the concepts that you need to be able to apply from mathematics to solve these wave functions. There's a lot of linear algebra, matrix algebra, a whole bunch of calculus, and even some differential equations are involved in quantum mechanics. So hard stuff well beyond the level of this class. So we're just going to kind of jump to the answers, the solutions to Schrödinger's wave functions, which are known as quantum numbers. Now, before we get to quantum numbers, we're going to talk about Heisenberg. Heisenberg is another big name in quantum mechanics. He came up with what's known as Heisenberg's uncertainty principle. And what the uncertainty principle states is that we cannot know to high levels of accuracy both the position and the energy of an electron at the same time. And in fact, as we learn more and more about the position of an electron, we know its energy less and less accurately. So it's kind of like a teeter-totter. As we know more about position, we know less about energy. As we know more about the energy, we know less about its position. And this is actually the reason why those orbitals we learned about in a previous lecture video, s, p, d, and f orbitals, are not actually the path the electron takes, but more of a giant area of high probability of where an electron is. We can't know exactly where an electron is in the atom, but we can take a little bit of a guess, right? We have a pretty good probability of finding them within those shapes. The s orbital being the sphere, the p orbital being kind of like the dumbbell look, the d orbital being kind of like a four-leaf clover, and the f orbital kind of like a big flower type shape. So this gives us a general idea of where they are, but we don't have an exact position. All right. Quantum numbers. Now, quantum numbers are the solutions to Schrödinger's wave functions that he came up with. And they tell us a lot about the energy and a small amount about the position of our electrons within the atom. I like to think of them as electron GPS, because if you know all the quantum numbers for any given electron, you have a pretty good idea of both the energy, we know a lot about, and then we know kind of a rough area of where we can expect that electron to be within the atom. So there are actually 4 different quantum numbers. The first quantum number is known as the principal quantum number, and funnily enough, we've been talking about it a lot already in this chapter, right? N is the energy level that our electron is hanging out at. So this was all what we talked about in video lecture number 2. So we've spent quite a bit of time talking about the principal quantum number. And let's talk about another one. We'll go through each one of these in more depth on later slides. So the next one is known as the angular momentum quantum number. And this one actually has to do with the type of orbital that our electron is hanging out in. They both have different symbols, right? All of them have different symbols. So the principal quantum number symbolized by a lowercase n. The angular momentum quantum number is symbolized by a lowercase l. And this brings us to our next one, the magnetic quantum number, which is symbolized by an m sub l, the subscripted little l here. And the magnetic quantum number we'll get into a little bit after we talk about the other two a little bit in more depth. And the final one is the spin quantum number, which is an m sub s symbol. All right, so we need to know their symbols, we need to know their names, and we need to know what they tell us. So we're going to briefly talk about the principal quantum number, and then we'll go through the others in more depth. I already kind of talked quite a bit about the principal quantum number. It can have any integer value from 1 to infinity. So I always make this joke for those Dragon Ball Z fans out there. You can even have a principal quantum number of greater than 9,000, or in other words, an energy level over 9,000. If you don't get it, YouTube it. It's an anime show. Nonetheless, N is related, or really not just related, but is the energy levels of the different orbitals, like in the Bohr model of the atom. The larger the N, the larger the energy of the orbital, and the larger the size of the orbital as well. So S orbitals are one of the 4 orbitals that we talked about last lecture video, and they're kind of like spherical. So a energy level 1 S orbital's a small sphere, and then energy level 2 S orbitals are slightly bigger spheres, and then energy level 3 would be a bigger sphere than that, and so on. And they just kind of get bigger and bigger, and also higher in energy, as far as like needing, the electron needs more energy to hang out in those higher energy levels. We call each N value by a special name. We call them electron shells. And that's just to kind of go, hey, if we're at an electron shell of 2, then that's one way of me telling you, hey, N is 2. But overall, we've spent last lecture talking quite a bit about N, so we're going to kind of move on. Okay, so the next quantum number is the orbital angular momentum quantum number, or just the angular momentum quantum number. Now, it's symbolized by a lowercase l. Usually it's a cursive L, but I just couldn't find a good cursive L font in PowerPoint, so I just went with the font of everything else. But usually a cursive L, lowercase. Now, what this quantum number actually tells us is really what type of orbital the electron is in. So orbitals in a given energy level and principal quantum number can be grouped into what we call subshells, the different types of orbitals. Now, so each subshell would be an s orbital, a p orbital, a d orbital, an f orbital. Those 4 orbitals we learned about earlier in this chapter. So each of those different orbitals has a different value for their angular momentum quantum number. All right, so you need to know these values and which orbital they correspond to for the first 4 angular momentum quantum numbers, and that's L of 0 is an s orbital, right? So when you see an L of 0, we know we're talking about an s orbital. When we see an L of 1, we know we're talking about a p orbital. When we see an L of 2, we know we're talking about a d orbital. And when we see an L of 3, we know we're talking about an f orbital. Now, there are L's higher than 3. You just need to know the orbital designation for the first 4, because these are the 4 primary types of orbitals that we're going to see in our class. The other orbitals that are possible are typically mostly theoretical, not so much in actual practice type scenario. So one of the things that you need to know about L, our angular momentum quantum number, is that it has a limit on what values can be present. And that value is any integer value from 0 to n minus 1. So if our principal quantum number is 4, then the L values that are possible would be 0, 1, 2, and 3, all the way up to n minus 1. And since n is 4, n minus 1 would be 3, but I have all 4 of these values present at this energy level, or possible at this energy level. If we're at energy level 5, right, the quantum numbers that are possible for angular momentum would be 0, 1, 2, 3, and 4. Now, we don't know what 4 is as far as what the orbital is, but we do know that it's a possible angular momentum quantum number, and we would have to include it, regardless of the fact that we don't know what type of orbital it corresponds to. Now, if you wanted to know, it's actually a g orbital, but we don't cover those because they tend to be very theoretical, and in most cases we don't see them. So you don't actually need to know that angular minimum 4 is a g orbital. All right, so if you have any questions, let me know. We have 2 more quantum numbers that we have to cover. They'll be covered in the next lecture video.